Question 3a. If m and n are irrational numbers where m is not equal to n, then mn is also irrational. Disprove this statement by means of a counterexample. There are many different ways you could go about it. I'm just going to show you one of them. So, for instance, root 8 times root 2 is equal to root 16. Root 16 is equal to 4. 4 is rational. Therefore, the statement is false. B, part I, sketch the graph of y equals the modulus of x add 3. So looking at this, B, part I, the graph of y is equal to the modulus of x add 3. So if I sit there and think initially, y equals x add 3, it's going to be a graph that goes through like that, passing through 3 at that point there. Now, this is the modulus of x add 3. It's not the modulus of the whole thing, it's just the modulus around the x. So this is saying there is no negative x. So what we can say is that this part is going to carry on because that's a positive x, but now it gets reflected across here, and that's my graph going through 0, 3 of y is equal to the modulus of x add 3. Any negative x values that would have existed are turned positive, and so they are just simply reflected in the y-axis. B, part 2, explain why the modulus of x add 3 is greater than or equal to the whole of the modulus of x add 3 for all real values of x. Now, if we just change colour slightly and draw over the top the graph of y is equal to the modulus of x add 3, then we can see that for a positive value it's going to carry on, and then this will carry on down and then reflect up like that. So what we can say here is, as is shown, y equals the modulus of x add 3 is equal to y is equal to the modulus of x then add 3 for x is greater than or equal to 0, because we can see that they overlap on the same part of the graph there. However, when x is less than 0, y equals the modulus of x add 3 is always below y is equal to the modulus of x add 3 as shown above. We can see that here, this part of the graph is always below that part.